Hi, it's Professor Jones again, here to talk about transformations of functions from section 2.5. So let's take a look. The objectives are to recognize graphs of common functions, use vertical shifts to graph functions, use horizontal shifts to graph functions, use reflections to graph functions, use vertical stretching and shrinking to graph functions, use horizontal stretching and shrinking to graph functions, and graph functions involving a sequence of transformations. Graphs of common functions, it turns out that there are 7 functions that are frequently encountered in this course, and those functions are f of x equals c, known as the constant function, f of x equal x, known as the identity function, f of x equal absolute value of x, the absolute value function, f of x equal square root of x, square root function, f of x equal x squared, the standard quadratic function, f of x equal x cubed, which is the cubic function, and f of x equal the cube root of x, which is the cube root function. So it is essential to know the characteristics of the graphs of these functions. So let's take a look at each of these functions separately. Here's the constant function and its graph. Now notice in the graph shown, this is what the graph looks like if c is a positive constant. It would be a line that extends into the first and second quadrant. However, c could be 0, then the graph would be simply the x-axis, or c could be negative, and in that case the graph would extend into the third and fourth quadrants. The domain of this function is all real numbers. The range of the function consists of a single number, and that's c. So notice every point on the graph has the same y value, and that y value is c, because f of x is the same as your y value. The function is constant on the entire set of real numbers. The function is even. So notice how there's symmetry with respect to the y-axis. And that's what happens when a function is even. Let's look at the identity function. Its graph is a line which makes a 45-degree angle with not only the x-axis, but also the y-axis. The domain of this function is the set of all real numbers, and that's also the range of the function. The function is increasing on the interval of all real numbers. So in other words, the function is always increasing. The function is odd. So notice what you see in quadrant 1, the mirror image of that is in quadrant 3. So you have symmetry with respect to the origin. The absolute value function is shown here. It looks like a V, where the point of the V is at the origin. So notice that the domain of this function is the set of all real numbers. The range of the function is the positive real numbers and 0. So notice that there are no y values in quadrant 3 and 4. So all y's are either 0 or positive. That's why that's our range. And the function is decreasing on the interval -infinity 0 and increasing on the interval 0, infinity. So in other words, when my x values are negative, the function is decreasing, and for x's that are bigger than 0, the function is increasing. The function is even. You have symmetry with respect to the y-axis. Let's look at the standard quadratic function. Here is its graph. Notice the domain is the set of all real numbers. The range of the function is all x's that are bigger than or equal to 0. All y's that are bigger than or equal to 0. The range talks about y. And so y's are either 0 or something bigger. The function is decreasing when x is smaller than 0. So here, as you move from left to right, the function is going downhill. And the function is increasing for x's that are bigger than 0. So as x is bigger than 0, the function is going uphill. The function is even. So you have symmetry with respect to the y-axis. Let's take a look at the square root function. Here is its graph. The domain is all x's bigger than or equal to 0. The range is all y's bigger than or equal to 0. The function is increasing for all x's bigger than 0. The function is neither even nor odd. So you don't have symmetry here at all. So you have to have symmetry in order to have evenness or oddness. Let's take a look at the standard cubic function. Notice that the domain of this function, as you look at its graph, is all real numbers. The range of the function is also all real numbers. And the function is increasing for all real numbers. So in other words, the function is always going uphill as you move from left to right. So in other words, if you're at a point on the graph and you move horizontally to the right, you have to always go up to get back on the graph. So when you're on the graph, you move to the right, you have to go up to get back on that graph. And the function is odd. You have symmetry with respect to the origin. So the portion of the graph in quadrant 1 has its mirror image in quadrant 3. And that's symmetry with respect to the origin. The graph does not appear at all in quadrants 2 and 4. Now let's look at the cube root function. So this function has a domain of all real numbers, a range of all real numbers, and the function is increasing for all real numbers. Again, to determine that a function is increasing, start at any point on the function, on the graph of the function, move directly right, and in order to get back on that function, you have to go up. So that indicates an increasing, where the function is increasing. If you had to go down once you move to the right off of the function, if you had to go down to get back on the function would be decreasing wherever that happens. This function is odd. The mirror image of what you see in quadrant 1 is in quadrant 3. So you have symmetry with respect to the origin. Let's talk about vertical shifts. Let f be a function and c a positive real number. The graph of y equal f of x plus c is the graph of y equal f of x shifted c units vertically upward. The graph of y equal f of x minus c is the graph of y equal f of x shifted c units vertically downward. Let's look at an example of a vertical shift. So let's use the graph of f of x equal absolute value of x to obtain the graph of g of x equal absolute value of x plus 3. So based on the definition of vertical shifts, we can see that g of x shifts f of x 3 units upward. So let's look at the graph of f of x. So we know that here's our absolute value function. We know it's this v whose point is at the origin. But when we go to graph g of x, notice that f of x, the only difference between these two is that I've shifted f of x 3 units up. Otherwise, they have the same shape. I've just shifted upwards. And because we can only see so much of the graph, now you can only see this lower portion of the graph because you've shifted upward by 3 units. So here you can only see this lower portion of f of x. All right, horizontal shifts follow a similar pattern, but there is an important difference that you need to be aware of. So if f is a function and c is a positive real number, y equal f of x plus c is the graph of y equal f of x shifted to the left c units. So when I'm adding c to my input, so my input is changed in that I've added c to it, that's a shift in the negative horizontal direction. So I've actually moved left. And y equal f of x minus c is the graph of y equal f of x shifted to the right c units. So let's look at an example. So let's use the graph of f of x equals square root of x to obtain the graph of g of x equals the square root of x minus 4. So notice that the graph will shift to the right 4 units, according to what we just talked about. We're changing our input by subtracting the positive number 4. So that's a shift to the right. So here's the graph of f of x equals square root of x, which is the standard square root function. Now let's look at what happens when we graph g of x, which shifts f of x 4 units to the right. So now so notice for f of x, when x is 0, y is 0. But now when x is 4, y is 0. So you're 4 units shifted. So the only change is that it's as if you've picked up this curve, turned it red, and moved it 4 units to the right. Reflections of graphs um, we have a couple of reflections that can happen. One reflection is the graph of y equal negative f of x. So when I have a function negative f of x, the relationship to the graph of y equal f of x is that I've reflected about the x-axis. Now, when I reflect about the y-axis, the change is made to the input. So y equal f of negative x is the graph of y equal f of x reflected about the y-axis. So when I reflect about the x-axis, I multiply the function by negative 1. When I reflect about the y-axis, I multiply my input by negative 1. The function's input is multiplied by negative 1. So let's look at an example of a reflection about the y-axis. So we're going to use the graph of the cube root of x, f of x equal cube root of x, to understand the graph of h of x, or to obtain the graph of h of x equals cube root of negative x. Now the graph will reflect across the x-axis, and that's what we just talked about. When you change the input by multiplying it by negative 1, you reflect across the x-axis. So let's look at, here's the graph of f of x equal cube root of x. Now let's look at the graph of h, which is the cube root of negative x. So we're going to reflect, that function's graph is going to be reflected across the x-axis. And that's what we see here. So notice that it's as if we just took it and rotated it about the x-axis. So this blue portion is turned red and rotated about the x-axis. And now instead of being in quad 1, this portion is in quad 4. This portion that was blue and in quad 3 turns red and is rotated into quadrant 2. So that's the effect of multiplying your input by negative 1. We can also vertically stretch and shrink graphs. So let's let f be a function and c a positive real number. If c is bigger than 1, the graph of y equals cf of x is the graph of y equal f of x vertically stretched by multiplying each of its y coordinates by c. If c is between 0 and 1, the graph of y equals cf of x is the graph of y equal f of x vertically shrunk by multiplying each of its y coordinates by c. So in other words, if c, say for instance, were a half, each y coordinate is half of what it was for the same x value before. So let's look at an example of vertically shrinking a graph. So let's use the graph of f of x equal absolute value of x to obtain the graph of g of x equal 2 times absolute value x. Okay, and this is actually a vertical stretching. That was a mistype So this is a vertical stretching of a graph, as we said previously. Our C is 2, and that's bigger than 1. So this is going to be a vertical stretch. So f of x is the absolute value of x. We recall that that's what that looks like. Now, because I'm stretching, I'm actually, so imagine you're taking the tips of the graph and you're pulling them upward. What would happen if you pull them upward? The graph is going to get skinnier. So let's look at the graph of g of x equal 2 times the absolute value of x. So notice how a vertical stretch actually makes a graph thinner than it was before the stretching occurred, as we see here. So let's look at horizontally stretching and shrinking graphs. If f is a function and c is a positive real number, and c is bigger than 1, then the graph of y equal f of c of x is the graph of y equal f of x, horizontally shrunk by dividing each of its x coordinates by c. If c is between 0 and 1, the graph of y equal f of cx is the graph of y equal f of x horizontally stretched by dividing each of its x coordinates by c. So the thing to notice here is that the change that occurs is to what you're putting into the function. So it's a change to the input, whereas the vertical stretch and shrink is a change to the output. It's a change to the y value when you're talking about a vertical stretch or shrink. Here it's a change to what you're putting into the function. So let's look at an example of this. So let's use f of x equal x squared to get the graph of g of x equal 1/2 x squared. So here's f of x equal x squared. And this is written wrong. The function is written wrong. Let's, in the top statement, let's change this. Okay, so we fix this problem. That square should have been on the outside. And so this is an example of what we were just talking about. Now, when we talk about stretching horizontally, you're holding the tips of the graph and you're stretching them out to the sides. So you're actually pulling them away from the middle when you're stretching. When you're shrinking, you're pushing them in toward the middle. So, in other words, this is going to be wider. The red graph is going to be wider than the blue graph when we have a horizontal stretch, as we have here. So when your C is between 0 and 1, you have a horizontal stretch. Okay, so that's an example of horizontal stretch. If that C would have been bigger than 1, it would have been a horizontal shrink, and the graph would have gotten skinnier. So notice that these physically, what we actually visually see is very similar to what we see with the vertical, but they're opposites. So let's look at using a sequence of transformations where we start with our standard x squared, and we want to obtain the graph of g of x equal negative 1/2 times the square of x plus 1 minus 2. So we've got several transformations going on here. So first let's look at the graph of f of x equal x squared. So there's our standard quadratic functions graph. Well, let's use the graph transformations in order. So first of all, we see that this negative 2 is a vertical transformation of a movement of 2 units downward. So the shape of the graph has not changed at this point. We've only vertically translated 2 units downward. Now the 1 in this parenthesis, where I'm applying the square to x plus 1, is a translation to the left. So I'm actually moving 1 unit left. So now let's take this black curve and let's move it 1 unit left. All right, then we want to shrink vertically, because that's the effect this positive 1/2 has. It actually shrinks the graph vertically. So in other words, it's as if I take the tops and push and fix the vertex and push the graph downward. So that's the effect the 1/2 has. So it makes the graph fatter than it was. You know, if you stay the same size you are, but you get shorter, you're going to be fatter. So that's the effect that had. And now the final transformation happens when we employ the effect of this negative sign, and that actually, remember, is a reflection. So we're going to take the graph that we've done these other 3 transformations to. We've shifted down, we've moved left, and we've vertically shrunk, and now we're going to reflect. And that will give us the actual graph, and we'll put that one in red. So there it is. So all we did was take this graph and reflect it, but notice the reflection happens at the horizontal line that passes through the vertex. So in other words, if I pass a horizontal line through the vertex, I'm reflecting about that line. So because I did the other transformations first, that reflection was about the horizontal line that passes through the vertex. But I could have done that reflection first, and then that reflection would have been about the x-axis. All right, so typically this is the situation that you're going to have a sequence of transformations rather than just one.